everyone, I welcome you back to another episode of Crash Chemistry Course. And today, in this episode, we're talking about radioactivity. Now, in radioactivity, we have different concepts to understand. Now, but basically, the history of radioactivity goes thus: in the late 19th century and in the early 20th century, the various scientists like Henry Becquerel, Marie Curie, Pierre Curie. So each of these individuals, they worked to develop and find out and discover many of these radioactive elements. Now, these radioactive elements, they are simply elements that disintegrate and decompose over time, and their rate of decomposition is unaffected by changes in temperature, composition, concentration, and pressure. So what that means is that whenever you have a radioactive substance here, it's the rate of at which it's decomposing will cannot be affected by anything. So, and that rate is an absolute value, and it is known as the rate of the radioactive rate. And that results in what is known as decay constant, and what is time of decay. That's half-life. That half-life is an absolute value of that compound. So what that means is that whenever you have a mass here, the half-life would never change. That means the half-life is the time taken for an amount of the compound to disintegrate to its half amount. So, and let me talk about these amounts that are disintegrated. What are they composed of? So, and these amounts that are disintegrated, they are composed of different particles. Example of those particles are alpha particles, which is denoted by the Greek letter alpha. We have beta particles denoted by the Greek letter beta. Then we have gamma particles. Now, each of these particles, they have their different properties. Now, for the alpha particles are simply helium atoms. That is 4,2 helium. So, and these helium particles, they are known as alpha particles with a mass of 4 and a charge of 2. Now, we have beta particles. Your beta particles are simply your electrons, and these electrons, they often have negligible masses, but they have a charge of negative charge of 1. Then you have your gamma particles. Your gamma particles, they are neutral particles, and they are basically in form of waves. So these gamma particles, they travel as waves. They don't have masses, and they don't have charges. They are neutral. Now, talking about these particles, they can be liberated from the substance. So, for example, whenever you have a decomposition and you have a degradation of something like, for example, let's assume we have an element being broken down, like radon. Now, these elements, there are different types of elements that can be broken down in radioactivity. You can have uranium, you can have radium, you can have plutonium, you can have polonium, and so on and so forth. So there are different types of radioactive elements, but a property of this is that each of them has their unique half-life, and they have their unique and they have their unique products which are formed. For example, when radon radon 224, 226, 88, 226, 88. When it breaks down to form 222 radon 222, 222 radon, and 86 radon. So basically, this radium decomposes, or rather disintegrates. It exhibits radioactivity to form radon, from radium to radon. So, and then whenever you have this, you can just take the difference in masses. This one is 226 minus 222, that will be 4, and this difference is 88 minus 88, that's 2. So you can know automatically that this particle being emitted is an alpha particle. Just put helium, the symbol for the helium atom. So, and this is known as an alpha decay. So anytime you have an element breaking down into another to form two or more elements, so that's those particles being produced is the decay of those particles. If we have another electron being produced here, that will form a beta decay, and if we have gamma waves being produced, we have gamma decay. So, and this is this concept that is used to make all these explosive known as hydrogen bomb, and all these atomic bombs. So these atomic bombs and hydrogen bomb, they are formed when you have these radioactive elements, whenever they decay and produce a large amount of energy, and there's what is known as critical mass. That is the amount of the mass of the compound that is able of catalyzing this explosive decay. So, and that is also an application of radioactivity. So next we're talking about the application of radioactivity, which will be, it is used in science, it is used in industry, and it is used in different ways. First of all, let's talk about the curative use, which is in medicine. Now, radioactivity is used in medicine to cure cancerous growth. Anytime we have cancer, at times you can use exposure to radioactivity to cure it. And even whenever you want to take an X-ray, you make use of an exposure to X-rays. And those X-rays, they are just like the gamma rays, but they are not really like radioactivity. But these rays, they are often emitted by radioactive substance. So these gamma rays and other rays that are emitted during radioactivity, some of them are used for curing cancer. Then we also have used in scientific research. And the reason why radioactivity can be used in scientific research is that most of the time our body does not make any differentiation between normal and radioactive elements. So whenever you feed radioactive particles to animals, the body, their body system reacts to those things just as if they were normal. So, and as a result of that, you can be able to use that to trace these the paths taken by these elements, and that's known as radioactive tracers. So these tracers, they are application of radioactivity. And lastly, we'll talk about industrial applications. And in these industrial applications, you basically use radioactivity to trace and then to look for leakages in metal and other materials. So for example, you can use it to look for leakages in pipes and so on and so forth. So that is basically radioactivity and applications of radioactivity. Thank you for watching.